Welcome back to the last session. So this session is all about practical case studies of the sort of assessment and strengthening. We've got three sessions here. That just jumped on its own, I think. We've got three case studies in this session. We're going to move straight into the first one. So we have three speakers in this first session, all from my parent home of Atkins Realis. So we have Kevin Drain, Homayoun Puya and Steve Salter. Quick introductions for each of them. Kevin's got 25 years experience in repair and rehabilitation of bridge and civil engineering structures across various industry environments, and he's developed solutions for asset owners across all sorts of types of contract, DBFO, DMB, local authorities and national asset owners. Homayoun's got over 20 years experience in the field of corrosion, concrete durability and repairs, and he leads a team specialising in forensic investigation of deteriorating concrete structures, giving advice on service life prediction and corrosion protection techniques. And finally, Steve has over 27 years experience in the inspection and maintenance of structures, with extensive experience in reinforced concrete structures suffering from reinforcement corrosion, and also installation of impressed and galvanic cathodic protection systems. So they're going to be presenting together on Redbridge Causeway, concrete repair and cathodic protection. And I think Kevin is going to kick us off first.
Good afternoon, everyone. Thank you for the opportunity to come and speak to you about our project down in Southampton, and good afternoon to everyone online. So, cheers. Okay, so just give you an overview of the Redbridge Causeway scheme. It's a Hampshire County Council scheme, so it's based down on the south coast. The contract was Milestone Construction, and as Chris mentioned, Atkins Realis was designer. The causeway itself is strategically important because it carries the dual carriageway of the A35 over the tidal river test near Southampton. It also crosses a number of network rail lines, local roads and local storage areas. And its primary function is to provide an access route between the commercial port at Southampton and the New Forest National Park, which are accessed at each end of the causeway. So as Chris mentioned, the project involved a range of concrete repairs, cathodic protection and re-waterproofing work to address historic defects. Now, one of the key challenges we faced was the client required us to keep traffic running over the top. And at 70,000 vehicles a day, this presented a very significant challenge. There is no local diversion route. It's a key causeway in and out of Southampton. To divert traffic, you have to take it north onto the M27 and back down the M271. To give us an additional challenge, the river test had a double high tide. So for those who've never seen one of these, what happens is the tide will come in, reach its peak, it will go out slightly, and then it comes back in. And the problem that gives us is the ebb tide, or the outgoing tide, then runs much, much faster than the incoming tide because it's got to move all that water out in a much shorter period. And then we had the usual utilities that you have in all your major bridges. And one of the other issues is there's no land. The causeway is completely surrounded with water. And then part of that water is a nature reserve. So looking at the causeway itself, this is an aerial view. Southampton's to the left as you look at it, the New Forest to the right. So the main structure is Redbridge Viaduct. This is where we've done extensive cathodic protection and concrete repairs. We've also got Redbridge East, where we did galvanic anode protection and concrete repairs. And on Redbridge West, we've also done a full ICCP system to the piers and concrete repairs. That's our compound. That's the only area available for our compound. So we're really constricted on land, which we can use for the works. These are the two rail lines that we're bound by just to make life a bit more interesting. And the client also wanted us to re-waterproof a fourth bridge at the same time. So just going over the structures. So the main structure, the biggest one, is a 20-span viaduct. It's a series of concrete beams, and the piers are continuous into the ground. We call them pile bents, where they come down the column, and that forms the pile foundation. Where those piers transition to on land, they become leaf piers with some post-tensioning, and that presented a number of problems for us when we do the cathodic protection. The key challenge we faced is it was an early example of reinforced concrete construction on the south coast, and the testing identified elevated chlorides in the pier legs. And as we said, one of the key challenges is The part we need to remediate is in this intertidal zone with these very fast flowing tides. So we need a lot of temporary works, which we'll show you in a minute, to address the works. Redbridge East is a modular arch solution, part over the tidal test and part over network rail lines. It was built around 1930, so it's getting towards the end of its serviceable life, and the client wanted to extend that period. And because of its form and its profile, we couldn't actually use any underbridge units to inspect it. So one of the techniques that we had to come up with is using turfers anchored to the concrete barriers, which you can see in the top right-hand corner, just to provide us access for testing and inspection. It's quite a complicated arrangement. Again, we've got major services and we've got elevated chloride in the tidal spans. And then the final major structure is Redbridge West. And as you can see from that top photo, there is no dry piece of land to get to it. It's all water-based work, making it more challenging. Again, the majority of the structure is 90 years old, and the client was keen to extend that period. And again, all the services that are on the other structures carry through on this. Same issues, elevated chlorides and spalling, and we had a number of potholes indicating the waterproofing had failed. So, just talking about the design challenges that we had to overcome. So the first one was actually getting to the structures to complete the work. As you can see from those two photos, there isn't a lot of dry land there. And that was one of our early considerations, is how do we actually do the work? So with Milestone as ECI contractor, we developed a system of pontoons and quick demountable scaffold, which you can see in the top picture, which we could adjust as the tide came in and out, and that enabled us a much longer working window than just working at low tide. The other issue we had is pontoons move. They move around with the wind, move around with the tide. So there's potential that when we're doing the breakout operation, a lot of debris would fall in the river test. And that's really important because we've got the nature reserve nearby. So what we did is we developed a system of netting, which you can see in the bottom right-hand corner, to catch any debris when we were breaking out. And because that netting is flexible, it would move with the pontoon, it would go up and down with the tide. The other issue where we couldn't use pontoons, we had to design the temporary works to be submerged, and we'll come on to show you some pictures of that. But that temporary works design was particularly challenging because of the high flows that we had. So to give you an idea of the scale of the access that we had to put in, the top left-hand picture is the main viaduct, and you can see all our temporary walkways, all our temporary access platforms. So the temporary works in itself was a significant engineering challenge. The top right shows the pontoons that we were using with the demountable scaffolds, and the bottom picture shows how we designed the platforms to be submerged. You can see the weed from the incoming tide. The other issue that we had was the working windows were very limited on the rail span, so we had to develop a way of getting in and out very quickly, getting the works mobilized and maximizing the possession window. So one technique that we found particularly useful was the spider mounted mutes. If any of you have never used one, I highly recommend you do on the railway because they can be deployed and recovered very, very quickly. And they can adjust themselves to a range of different levels and ground conditions. So the next challenge that we faced was with all these different structures, with the number of repairs that we had, it was very, very difficult to identify how many overall details we would need. When we started counting them up, we were looking at thousands and thousands of different details that we had to prepare, which isn't practical in the sort of funding levels that we get from our clients. This was made even worse when we considered the phasing that we needed to do to maintain traffic across the bridge. And we also had to consider what the follow-on cathodic protection guys were going to do with their works as well. So there's huge numbers of details, huge potential impact on the work if one of those details didn't work. So one of the solutions we came up with was developing a range of standard repair details, which the contractor could adopt and then could adjust to suit. We also gave a number of standard rules for reinforcement repair, again, giving the contractor the freedom to make small adjustments on site so that you didn't need the interface with the designer, which would then slow down the works and cost a lot of money. And then just communicating the phasing of the repairs. As I mentioned, we have 70,000 vehicles running over the bridge each day, so we needed to do works in a staged order in order to make sure we didn't weaken the structure. So here's just an example of some of the repairs that we did. So on the left-hand side was a standard repair to a spall where the reinforcement's exposed, a standard repair to a spool where no reinforcement is exposed, and a standard crack repair detail. So this enabled the contractor to make little adjustments on site in conjunction with the designer site representative, but you had a standard suite. You didn't need to keep coming back to us, and we weren't then the bottleneck for the works. The top left is an example of some of the reinforcement detailing rules that we gave them. So we gave them a range of corrosion. If corrosion is X, this is what you do. And on the right, we also set in standard tolerances through the work. So keeping everything standard reduced the amount of design information we had to produce, and it made it easier for the contractor to adjust things on site to his actual site conditions. And then the final point was about communicating the phasing. So with these giant structures with lots of complicated phasings, we had to come up with a solution on how to communicate that to the contractor. So every defect had its own reference, which you can see on the elevation. And then what we did, we used color coding to indicate which phase works were undertaken. So you'll see the orange and green bars or the red and purple bars on that elevation, and they give a visual representation to the contractor of when he's doing work. And then what we did for the key details, we did a little key plan for him showing how each of the repairs was to be built up across the phases. And we carried that color coordination through. And that was a very simple way of helping the contractor to understand what to do, when to do it. So I'll pass over now to Homayun, who will take you through some of the cathodic protection issues.
Afternoon all. As you may know, the steel reinforcement in concrete is generally protected by the alkalinity in concrete, and because of the formation of the very dense, oxide layer. So once environmental elements like chloride and carbonation actually start to kind of diffuse actually into concrete, then the anodic and cathodic actually sides start to form. In the anodic side, effectively iron get dissolved into the pore solution and release an electron, and those electrons actually has to be consumed somewhere, which is the cathodic side. And as a result, basically the iron get dissolved and basically get oxidized, to different form of oxidation, and that's where we get the kind of expansion, expansive corrosion products, and that's the main cause for crack, delamination, and spot in concrete. So cathodic protection is an electrochemical technique proven over the years, recognized by BSCN 12696 and also National Highways standards, effectively by applying a DC current within the concrete and around the reinforcement. We're trying to kind of reverse, those reaction, the anodic and cathodic reaction. So effectively, we are connecting the negative side of the DC power supplies to the reinforcement, and we're passing the current using inert anodes. It could be titanium or conductive coating, etc. And the current which is flowing from the anode, which is the positive side, to the reinforcement and back to the power supply, effectively we are shifting the half cell potential of the steel to the safe and immune kind of zone. Hence, basically, steel corrosion actually will be stopped or minimized in a sense, and the rate of the corrosion will be reduced quite significantly over the time. And in order to basically prove that the system is working and protection is provided, we are monitoring the CP system using a number of probes like reference electrodes or decay probes, and basically to maintain and monitor the system over the time. So for Red Bridge Viaduct, basically, and any CP system installation, there are a number of challenges. First of all, as you can imagine, embedding all those anodes and cables, within the concrete to be chased or to be even surface mounted is a challenge. And breaking out the concrete, chases, to embed the concrete typically tend to cause weakness, into a structure. So that's the challenge that we need to face. Secondly, the system actually should be basically maintained and switched on, all the time to provide the protection. And also the system has to be designed in a modular way, so it can be installed, in phases, depending on the access provision. And also Zoning the system is very critical because depending on the exposure condition of, at different elements, the current demand will be different. Hence, zoning the system and controlling each zone individually, that's one of the key challenges. So basically, as part of the solutions for the Redbridge Viaduct, we divided the CP actually system into 40 zones, basically across the elements. And in terms of installation of the anodes, we try to, for example, in case of the discrete anodes, we try to basically drill the anode from one face of the column or bearing shelf or crossheads to avoid redundant and basically multiple holes and damage to the structure. And for the large basic elements like a leaf pier, we use the mesh and overlay system to avoid the hands-arm vibration risk, which you may need hundreds of the holes and basic drilling to be done. And then, as I said, each zone actually can be independently controlled and switched off as and when needed. So regarding the zonings, these are the typical zoning that we use for the pile bends, as Kevin mentioned, the piers and the leaf piers. So part of the structure obviously was a tidal, so the current demand in the tidal zone because of the salt and the moisture in concrete actually was higher. Hence, those zones has to be maintained, separate and controlled, different compared to the atmospheric part of the structure. And also the bearing shelf, which was actually just below the joint and exposed to the leakage. Again, the current demand basically was different. And also the anode system for the bearing shelf was different, for example, from the rest of the leaf pier. Hence, the zoning actually was very critical, for that structure. These are the couple of typical standard detail of the installation of the discrete anode, for example, on the left. So you could see 2 rows of anodes basically installed into the crosshead or basically or part of the bearing shelf as well. For the large surface areas, you could see the basically leaf pier has been surface prepped using the water jetting, and then the mesh, the titanium mesh basically has been pinned using plastic pins to the surface. Once all the cables installed as well, then the whole thing actually will be covered in a sprayed applied mesh and overlay system, which the photo in the middle is the final product ready for energization and operation. Again, challenge about cabling, you could see the size of the cable chases that we had to cut actually. And also, in order to avoid delamination and debondment of the repair mortar basically within the chases, spacing between the cables actually was very important. So just to allow for a spacing and the number of cables to be chased is always a challenge, especially if you have a low cover areas, at the reinforcement, which basically we had to overcome. In terms of the control equipment, the photo on the left is those 2 cabinets on the left are housing the individual power supplies, which you can see the inside of basically cabinet, individual power supplies, the computer, the communication, the modem, and everything basically will be controlled remotely. So you can log into the system, adjust the current, monitor the system, and basically control, and maintain the system. And on the right-hand side, you could see the AC cabinet because the system is kind of main powered. So the AC power basically should be supplied all the time in order for the system to operate properly. One of the challenges that we had at 2 piers of the structure was the interaction between CP system and the high tensile, PT system, which was installed at top of the piers. As you may know, the high tensile strength and high stress steel can be affected by basically the high negative basically potential. And the high potential actually can basically kind of generate hydrogen atoms and molecules within the matrix of the steel, which cause fracture and basically sudden failure. So CP, in a sense, interacting with high tensile strength in a bit complex way, because on one hand, it's kind of generating the hydrogen. There is a risk of hydrogen evolution, but on the other hand, increasing the alkalinity around the reinforcement as well, which basically helps, the hydrogen controlling, this phenomenon. So as a result, there is a safe limit, which has to be determined by testing, the steel. For example, in this case was a McAlloy bars, but because of the condition of the system, the condition of the bars, and the practicality, we couldn't take a sample and test it. Hence, at the end, decision was made to reduce the scope of the CP system to avoid failure of the PT system. In terms of the monitoring, the key basically point about CP system is maintenance and monitoring. You cannot just leave the system running, because if the potential exceeds certain limit, you start to damage the steel rather than making any good. So this is a typical monitoring graph basically for the CP system for one of the zones. The test that we use in accordance to BS 12696 is the depolarization test. So effectively, we switch off the system for a period, typically 24 hours, and we monitor the potential decay of the reinforcement over that period. And there is a limit that we need to satisfy. It's a kind of practical and theoretical limit that basically that shows the system is operating properly and the steel is fully protected. Just to touch base on the power consumption, we get this question actually quite a lot. The fibUK had basically 40 individual zones, and the current demand or power demand was about 1.5 kilowatts. And in practice, we found that the system normally runs at about 50% of the capacity. And the cost of that over 1 year would be about £1,900, basically, which it may sound a lot, but compared to the maintenance and the concrete repair works, ongoing concrete repair works actually basically nothing and insignificant. Over to Steve.
Afternoon, everybody. Just going to look at a couple of slight details. This particular slide shows Pier 8, which is a pier that had a particularly large delamination on the base. You can see the yellow arrow pointed to it there. This presented a problem both in health and safety, in that there was potentially a large amount of concrete that could fall, and plus it needed to be removed so we could attach the scaffold anchor plates, which is what's shown in the red squares on the bottom picture. This picture shows the same pier, but at the base. This is the mast off area, is where the anchor plates have now been covered, ready for the overlay to be sprayed in place. And the bottom detail is what we call a tuck detail. What you don't want is the overlay finishing flush with the surface of the material, because then it can delam back up. So this tuck detail tucks the overlay into the surface, and then the detail at the bottom just provides an arris on the corner to prevent spalling. And that is the finished product. You can see the overlay. Different colors because of different phases of work. So some of the lighter stuff is a lot newer than the other material. A couple of details here. The top one is a positive connection, and the bottom one is a negative connection. The positive connection involves the spot welding of a titanium rod to the titanium conductor, and also the mesh to the conductor bar, which you can't really see in that picture. And then the black cable coming in is actually heat shrink, which is connecting the copper cable to the titanium rod. Vital that is airtight, and the heat shrink used is adhesive lined to prevent that oxygen from getting in. And then the negative connection at the bottom is a similar thing, but there's a welded stud on the bar that's beneath that blob of epoxy. And then the copper cable connecting on either side is again heat shrunk to prevent the oxygen getting in and causing corrosion because of dissimilar metals. In the top picture, you can also see how aggressive the surface prep is. Using an overlay system, grit blast isn't sufficient. Early systems tended to debond. With this, we use what's called a roto mill, and that gives you a very aggressive finish, which has proven so far to give a very good bond for the overlay. This is showing a detail of a standard concrete repair. You can see the corroded reinforcement, and in the far right, you can see the bar that was clearly cathodic, which is in fine condition. And also, this is an issue that we found on site, was the shutter anchors were pretty much largely discontinuous. So that was an element of work that wasn't included for initially. So all of those had to be found and made continuous with the reinforcement, otherwise they would have corroded. And if there's an overlay, it would have blown the overlay off. And then on the other side, there's a couple of additional brackets we had to add on. Again, because they're going into the concrete, they would be affected by the CP. We had to stop the mesh short of the bracket, which is what the channel around the bracket is showing. And then the black cable hanging out is ready for a negative connection. So all the brackets are linked together with a continuity bar and then connected back to the system negative. So again, nothing will corrode within the system. Cable tray and connection box. The cable tray we selected was GRP. That removes any long-term corrosion risk. Stainless would have been good, but it's expensive. Galv is always a problem in the long term. And where it crossed expansion joints, we needed to leave a gap in the tray. Otherwise, in the summer, particularly when the bridge expands, you can find on sites where this hasn't been done that the tray starts to bow. It usually goes back again in the winter, but it's something we wanted to avoid on this site. And an eternal problem with lots of bridges is birds. So on the top of the tray, we had to put the pigeon spikes to stop roosting, which obviously aesthetically looks bad, and it could lead to premature deterioration of the GRP. On the bottom, we have a connection box. Here we would have normally done a junction box, which is a set of terminals, but because the access was so poor here, we felt that a connection box would be better. So the cables are simply crimped inside that box. You've got the field cabling coming in from the concrete on the left, on the right, sorry, and then the multi-core cables go out onto the tray and back to the TR on the left-hand side. And then that's over to you, Kev.
So the final site issue we wanted to discuss was something we're seeing a lot of clients ask for on recent schemes, and that was the verification of the bond between the repair mortar and the substrate. Now, there is a test methodology in 1542, but it's predominantly lab-based. So what we've had to do is develop a system where that can be applied in the real world. So what we do is we've done 50mm diameter cores to replicate what's in 1542, and we're looking for 3 minimum successful tests from each batch. And what we've done in the top left-hand photo that you can see is done a line of 3 for 7-day strength and a line of 3 for 28-day strength. Now, one of the challenges that we've seen on a lot of jobs is the contractor tries to do the sampling at an overlay which is too thick. And when they've tried to core the sample locations ready for the pull-off test, what they're finding is that the core is breaking while they're drilling the core out. So one of the techniques, if you get asked to do a bond test, is to try and minimize the thickness of the test sample so that when you core it ready to do the pull-off test, you're not going to fail it during coring. So 1542 records a depth of 100mm. So what we've had to do, this is a recent scheme for National Highways where we've done this, we had to include a box out in the overlay to do the testing to make sure that the depth of sample wasn't too long, so it broke off during coring. The other issue that we frequently see on pull-off tests is the debonding of the test dolly from the sample. We've seen a range of different adhesives used. I think we've gone through everything in the Screwfix catalogue now. But what we found is most effective is Hilti Hit 500 resin. So if you get asked to do this, don't bother with anything from the contractor says, banter in to go and spend some money on some proper Hilti Hit adhesive. And you'll see from the bottom 2 photos, that's been quite effective for us in actually achieving the pull-off test. Otherwise, the dolly will just separate off. So what we have now is a short video. This was prepared by Hampshire County Council for their residents, but it hopefully shows you everything we've talked about, what it actually looks like in practice.
So I'm here on the Redbridge Causeway, taking a look at the work we've been doing over the last few years and seeing what is yet left to do. I'm really sorry that there's been disruption and inconvenience for people as the lanes have been closed. Hopefully this will tell you a little bit more about why that's had to happen.
We're at Redbridge Causeway, which carries the A35 in and out of Southampton. We've got 4 bridges at this location. The bridges themselves are actually getting on a bit now, 100 years and almost 60 years. They are showing signs from the harsh environment here. The salt water in the air has actually got through the concrete into the reinforcement which is embedded in the concrete. That then rusts away, and as it rusts it expands, and that actually pushes off the concrete. So when we came here originally, there were a lot of locations where there was cracking, concrete had actually moved, and we could see the reinforcement. So we're actually repairing all of this, because if we don't, then the structure loses its capacity and we'll end up with having to put on permanent lane closures, and if we did nothing at all, then eventually the bridges would actually have to be closed.
So without doing any work, the bridges would fall down?
Yes, gradually, yeah.
Okay. The reason for us having to put lane closures in place across the bridge is why at the moment?
Well, the bridge on the other side, like built in the 60s, has a little bit more reinforcement, not as much as we would put in a brand new bridge these days, but these older ones built in the 30s, they have very little reinforcement within them. So as soon as that starts to go, we get problems with capacity. All of our repairs have been phased so that we can keep traffic moving, but it's a much bigger challenge on this side because the bridges are much older, and clearly we don't want to break out more and risk one of them collapsing. So we've had to do it phased. We've had to release all the loading on it by putting them down to one lane of traffic going across.
So put in simple terms, having too much traffic going across at the minute could endanger the bridge because we're having to take away some of the concrete to renew it.
While we repair it, we've got to reduce the loading on it.
When it's done, what is the outcome? What do we have?
We've repaired all 4 bridges, they'll all be done, and the repairs will see it through for the foreseeable future.
In the time it's taken, we could have built a new bridge. Could we?
You certainly couldn't get in a new bridge. You would have to take these ones down. That would take all of the route out completely, and it would take many, many years to do that. It would also cost an absolute fortune to do it as well. This site actually poses an awful lot of problems, actually, because we've got tidal water, so we have to work around the tides. We've had to do out of hours working, because obviously the tide changes all the time. We've got the railway just over there as well, and we need railway possessions for that. Some of those possessions are at night, so we do have to do night time working, but some of them are during the day as well, so we've had a mixture there. We couldn't work 24 hours because we wouldn't be allowed to from the noise point of view. But particularly at this end, we're very close to residential properties, and we have got it all shielded out, and we've got noise curtains up, but even so you can hear now the water jetting that's going on is a noisy operation.
So hopefully that's explained to you how important this causeway is and why we need to replace it. It also has shown you why we can't have 2 lanes open, but it is for a good purpose. At the end of this, we'll have a bridge that is fit for the future. So thanks everyone for your patience, thanks for looking for alternative routes, and thanks for sticking with us while we get this work done. So I'm here.
Okay, so that brings us to the end. So any questions?
So our next speaker is Chandan Gowda. Chandan is a chartered engineer, also at Atkins Realis, and he's contributed a range of complex structural assessments and infrastructure projects, including the main cable capacity evaluation of the M48 suspension bridge, structural assessment of the approach viaducts on the Forth Road Bridge, and FRP strengthening of a hotel for a confidential client. Prior to joining Atkins Realis, Chandan conducted research as a postdoc fellow on the use of fibre-reinforced polymers for strengthening RC structures, and he's going to be presenting to us today on the M25 Junction 3 Swanley interchange CFRP strengthening. Over to you, Chandan.
Thank you, Chris. Good afternoon, all. Just one more to go after me, so we're almost there. I'll be presenting one of the works which we have carried out in Atkins Realis, which is the strengthening at Swanley interchange, which is part of M25, and it's a junction 3 using carbon fiber reinforced polymers, which has been stressed quite a bit today. I believe most of us in this room have an idea now FRP strengthening using NSM and ABR. So I've divided the presentation into 5 parts. Firstly, an introduction where I'll give a brief background about the requirement of strengthening, followed by the design details, then the trials and experiments which have been carried out for the strengthening which was to be applied on live site, then finally strengthening followed by the conclusions from the work. As said, M25 is this ring which runs around London, and this is Swanley interchange junction 3, which is located between south, east and east of the M25 Central London. There are two structures here, two bridges. This one is the West Swanley Bridge, and the piers which you can see at the back is the East Swanley Bridge. It's a reinforced concrete structure. The back spans are only reinforced concrete slabs, and the central span is reinforced concrete with the beams, and it has piers, inclined piers supporting the structure. The structure was built in 1976, and immediately as soon as it was open, they noticed flexural cracks in the soffit on the back span and on the parapet locations on both the structures. So they realized, after doing investigations, they realized that the structure is under-reinforced. So they carried out strengthening in 1977 using bonded steel plates at both locations, on top of the piers in the hogging regions and at the back span supporting the sagging locations. According to current standards, CS 470, management of substandard structures, there was 6 monthly visual inspections carried out on the structure. And in one of the inspections in 1994, they found that the infill mortars around the top plates was missing. And the fixing bracket, which holds the steel plate, was also missing. So repairs were done in 1995. And the following inspection in 2017 and 2018, they carried out some hammer tap surveys on the exposed plates to see if there's any debonding between the plate and the concrete, which confirmed the debonding, and there were evidence of surface breakups as well. So as a first step, there was an optioneering study carried out to see which type of strengthening needs to be carried out on the structure. There were multiple options which was explored, and I'm not getting into the details of this optioneering study, but FRP was chosen as the strengthening technique. Here on the left image, you can see the waterproofing layer peeling off from the surface, and this is the infill mortar next to the steel plates, which is having issues. So the exact reason of this debonding is not confirmed, but we suspect all this has contributed for it, which is the raised level of strengthening when the steel plates are installed on top of the concrete deck, which reduces the surface thickness. Improper grouting, as we saw in one of the images. Then absence of waterproofing around the plates, and also due to the hydrostatic pressure of the axle loads, which keeps accumulating or happening on top of the steel plates. So all these reasons are the reason for debonding. So then, as I said, optioneering study was carried out, and then FRP was chosen as the technique to increase the structural capacity of the member. Technical report TR55 is a design guidance for concrete structures using fiber reinforced composite materials. There were two presenters today who had mentioned this TR55 in their presentation. One was John, and the other one was Professor from Brath. So we use this in the UK for strengthening the structures. And if some details are missing there, then we go look into FIB Bulletin 90, 14, and 40, of which Professor Sen is a contributor. Yes, he's contributed a few chapters in it. So for this structure, a total of 180 CFRP rods were used. Each CFRP rod had a diameter of 12 mm, and each rod was 14 meter in length. And they were spaced at 85 millimeter and 150 millimeter. A groove size of 20 by 20 millimeter was chosen. The FRP bar had a tensile strength of 2000 megapascal. In total, 2.2 kilometer of CFRP was used to strengthen the structure, along with 1.4 tons of resin. Quite a bit. This is the elevation of the plan. The blue line indicates the piers, and the red line indicates the steel plates which were strengthened in 1977. These are the hogging regions on top of the piers. And the goal of this is to move from left to the right, where, again, the red dashed line indicates the steel plates, And on the right, the dotted lines or the dots, green dots indicate the FRP element. So in the process of moving from left to right in the previous figure, there was plenty of experiments which were carried out by Octavius offsite trials. And this was carried out in 2018. And what did these optioneering study involve? The first one was, do we need to use FRP plates or do we need to use NSM bars? The FRP plates are not that far off than the steel plates. The only advantage is that the thickness of this element is much lesser than the steel plates. Whereas in the previous session, Professor Sena presented, the advantage of using the NSM is that it has a better bond with the concrete element, and it takes less time to apply on the structure. Whereas for the FRP plate, the surface preparation takes a long period of time. And the other trial was to see if we need to use the mill cutting or the saw cutting to execute the grooves for the NSM bars as well. Then the surface preparation, if we had to short blast or just the smooth surface finishing of the concrete was enough. So we also carried out some pull-off tests on both the surfaces. Then hammer tap survey was also checked along with the ground penetrating radar and ultrasonic test to see if we have any voids in the resin, even though it's not a standard technique, but we still tried to see if we could capture something, but we were unsuccessful. We also explored the groove size to varying between 15 mm to 25 mm, both in horizontal and in vertical depth. Because we don't have any standard method to measure these voids, the next best option was to carry out the destructive testing. So you cut the slab, which has been prepared off-site, at every 2 meters or 3 meters, and you check if you could find something. It was a positive result. There were no voids identified. So considering all this, NSM bars were chosen for better quality. And as mentioned, it reduces the time span for carrying out the strengthening on site. And this played a vital role because one lane of the carriageway was active when the strengthening was being carried out. I know in the next slide, there's one person who will be really happy because he's been pointing out that the glass transition temperature is not being considered in the codes. So that's one of the tests. Because the shortage of information, we had to check, especially because there are 2 layers of hot rolled asphalt, which is going to be laid on top of the strengthened element along with the resin. So this resin should not reach this glass transition temperature, because if it does reach, then it's not being effective and participating in the load carrying capacity. So what we did is we casted a 500 by 500 mm slab. A groove of 20 by 20 was executed and the strengthening was carried out. Then after 24 hours, a hot rolled asphalt before laying that, we had thermocouples which was installed on top of the resin, center of the resin, and at the bottom of the resin. Then a layer of waterproof was applied, and then one more thermocouple was installed on top of it. And then a 50 mm hot rolled asphalt on top of this waterproofing layer. Then we waited till the ambient temperature was reached. And once the ambient temperature was reached, then we laid another 50 mm of the wearing course on top of this binder layer. Then again, we waited for the ambient temperature. These 2 graphs represents the results. The left graph shows the evolution of temperature along time when the binder layer is applied. And the graph on the right shows the evolution of temperature when the wearing course is applied, which is the topmost layer. The particular curve which we are interested in here is the gray one, which shows top of resin. And then the yellow one is on top of the waterproofing layer. As we can see, the difference is quite high which shows that the waterproof is very effective in curbing this temperature. And then the top of the resin reaches close to 60 to 65 degrees for a very short period of time. And the glass transition temperature of the resin was 65 degrees. The right figure, when the wearing course is applied, the temperature at top of the resin reaches close to 40 degrees. Because when the binder course is applied and the temperature does reach 65 degrees, there is a short period of time, roughly close to 20 minutes, where the resin is not effective. When the resin reaches the glass temperature, glass transition temperature, it becomes more like a rubbery thing and is not effective in carrying the capacity. So the solution was to carry out, to apply the binder course in sequence. So at least we have the minimum load carrying capacity on the bridge when the binder course is applied. For example, when we put in FRP bars throughout the structure, we only apply the resin, we only apply the binder course on top of here. This section and this section is not applied. So these bars are effective in carrying the live traffic. And then once this binder course reaches the normal ambient temperature, then you apply this one, you wait for ambient temperature again, and then you close it off by applying in the central one. In this way, you continue to carry the live traffic loading on the structure. Whereas when we had to apply the binder course, it was not an issue as the maximum temperature what we reached was 40 degrees. Once we completed all the trials and we were confident that this could be executed on site, then we moved onto the site. The first step was to set up site offices, storage units, get a TM chapter vehicle, survey and mark the extent of strengthening, monitoring equipment, local grade baselines. Then the second step was to remove the surfacing, where the pavement and the verge strip were removed to expose the strengthening plates. Then there were white lines which was installed to identify where the steel strengthening was there and it wasn't, as we saw in one of the earlier pictures. Then we installed the temporary vehicle road system. Then a survey of strengthening plates were carried out for records to see if what's the amount of debonding that we have. So this is the first step where we have the grout removal. And this picture shows the hammer testing of the plates, where we have identified the debonding of the steel plates from the concrete surface. And this is the underside of the removed steel plate. This is the process of removal, where they're removing the steel plate one by one. Add something. And this is the post plate removal at the location and close inspection of the surface condition of concrete. So because we had to maintain minimum structural capacity of the structure, the strengthening had to be carried out in sequence as well, where only part of the plates were removed. And at those locations, the FRP was installed because this carriageway was live, carrying traffic. So the condition of the concrete was inspected, and then the repairs were carried out as planned in sequence. These are the grooves which have been executed on those specific locations. And it was done using this machine, which was specifically developed for the purpose. If we can imagine executing 180 grooves, 14 meters in length, it's quite a bit of an ask to execute these grooves manually. So, and also we would like to have it as straight as possible, because any inclination, then your FRP is, you create a local stress point over there. Again, just a refresher, we have to move all the way from here to here. And this is where we have completed executing the grooves with just 3 plates remaining in each section. So we have that minimum capacity in that section. This is the shot blasting preparation to make the surface rough. So we have a good bond with the waterproofing layer and the concrete surface. Just to check to see if the CFRP rod fits into the groove. And then you install 1/3 of the groove with the resin. You install the bar, and then you fill it up along with the sand carpet. This is the completed first phase. And then we give a gap of 24 hours overnight. So the resin sets in. And then this is the next phase where we are removing the central plate and the plates at the extremes. The same process is repeated. Execute the grooves. This is the mixed resin. Shot blast and apply the FRP. Once the whole process is completed, then we install the new deck waterproofing, then reinstate the curb lines, and then finally complete the verge with base layer and mass fill. For this case, we come for sequence application of the binder course, as we saw in the trials and experiment section, where only central strip was applied with the binder course, and then you wait for the temperature to reach the ambient temperature, and then the other 2 sides were applied with the binder course, whereas for the wearing course, it was applied in a single go. Finally, remove all the TVRS, or temporary vehicle restraint solution system, then reinstate the verge and the road surfacing. Refresher again. Step 1, mark out all the extents, remove the surfacing, check for the plates, remove part of the plates and install the FRP, followed by remove the remaining plates and install the FRP. Then once it's all set, apply the surfacing and then the markings. So we finished one side, it was open to public, and then we repeat the same procedure on the other side. But in this case, we move from here to here again. Just a comparison of both the figures, where you can see here the strengthening is done, whereas in here, just the FRP plates have been exposed. And this is the initiation of stage 2. And then the same procedure is repeated again. And all the road markings are back to the original state. So in conclusion, strengthening was successfully executed in 90 days. Challenges what we faced? Multiple, but to point out, one lane was open during strengthening, so there was less disruption to public. Glass transition temperature of resin was one of the challenging ones. There was compatibility between the resin and the waterproofing with kin-drained sand, which improved the adhesion. Our client was happy with the executed works, and we published a paper in SMART conference in 2024. So with this, I come to the end of my conclusions, and I'm open for questions.
So our next and final speaker today is Jan. Is it Jan or Jan? Jan Anil. Sorry, I should have asked you before. Jan is a structural engineer at Borough Happold, who's developed a specialism in the forensic assessment of existing RC frame buildings, and in particular, issues related to punching shear and transfer elements. And this has included the use of advanced nonlinear analysis simulations in collaboration with specialist firm ASDEA. He has extensive experience in remedial strengthening design methods, including through bolts, RC jacketing, and externally bonded reinforcement plates, to name but a few. So Jan, you're going to be presenting on existing RC frame structures, advanced assessment and strengthening techniques. Over to you.
Thank you for inviting me to speak. I hope you're all very well, and I hope you find this interesting. So I've been dealing with a lot of issues, defects in existing buildings related to punching, shear and shear in RC flat slabs, RC beams and RC transfer slabs. And over the years, I've got quite a lot of experience with rectifying these kind of issues. My presentation is split up into two parts. The first part, I will talk about some typical physical strengthening methods in relation to shear issues in reinforced concrete. And then the second part, I will discuss the use of advanced nonlinear finite element analysis, which can be used to gain a more accurate understanding of the behavior of existing concrete and tap into potential reserves of capacity in relation to shear and punching shear. And in some cases, avoid very disruptive and expensive remedial strengthening. So why is all of this important, and why do we go to above and beyond in terms of analysis to optimize these remedials and avoid them? There's a growing demand to reuse buildings. There's also a growing demand to expand the lifespan of existing building stock. There are also lots of defects in existing buildings, which I can't give specific details of, but they need rectifying, and this is something I've been dealing with a lot. There's also the Building Safety Act and sustainability drivers playing a role in all of this. At the same time, there's growing computer power and emerging research in advanced strengthening and assessment methods. And given the high costs of interventions in existing buildings, this warrants harnessing this power as an industry. So I'm starting with some typical strengthening methods, three common ones: post-installed shear reinforcement, typically threaded bars installed through the thickness of the slab. Other strengthening includes installing steelwork frames to add additional support, and these are normally jacked to engage them in that support. And people have already discussed this a few times, but externally bonded reinforcement techniques. For all of these, there are some overarching considerations, and I'm mainly talking about this in relation to existing buildings, some of which are occupied. The most obvious one is spatial constraints, where the buildings weren't designed to have strengthening, and trying to maintain the architectural function of the space and avoiding MEP services or diverting these where required. Another important consideration where working with existing buildings which have already got locked in stresses and established load paths is whether you need to activate the remedial. For example, do you need to preload the post-installed reinforcement? Do you need to jack the remedial strengthening steelwork structure to engage it? If you're installing externally bonded reinforcement, does it need pre-stressing, or should you jack the structure up before you apply the externally bonded reinforcement and then deprop it to actively engage that reinforcement? Another challenge I found is structural fire protection, and in particular for resin adhesive products, such as externally bonded reinforcement. They have a very low limiting temperature in fire. So either you have lots of fire protection, or you need to see that they are not required in a fire limit state. Also to be considered, if you're drilling lots of holes to install through bolts and those are being drilled through under strength slabs, do you need to prop? Do you need temporary propping? What are the logistics of installing that propping in an occupied building? Can you avoid propping and install the bolts in a hit and miss sequence, etc.? And then there are some other general considerations with regard to limiting disruption in existing buildings with noise and dust, maintaining fire escape routes during the work, figuring out how to deliver all the steel work into the building, how many splices you need, etc. So through bolts is probably one of the most common methods I've seen for strengthening slabs for punching shear. There are different configurations that can be used, such as some of the examples shown on the slide. The most common one is referred to as a through bolt, but normally it's a threaded bar, which is drilled through the full thickness of the slab. This is mechanically anchored by a wash of bearing plates on the top and the bottom. And you can preload these by using a calibrated torque wrench to preload the bolt and actively engage it. Normally for fire protection, the top is protected with a fire mortar or a screed poured over the top of the bolt. The bottom part of the bolt can sometimes be fire protected with these special ceramic caps, which are simply screwed on the end of the threaded bar. They are easy to install and could be concealed in the ceiling, such as shown on the picture. Otherwise, you need to use something like fireboarding, but that can be much more difficult to install. Sometimes it's not possible to have the bolt go all the way through. For example, you don't have any floor finishes or you have a lack of floor build-up. Sometimes it's possible to use a recessed bolt head at the top, so the top washer plate is actually recessed within the thickness of the slab. To preload, this can still be done. You can incorporate a locking key device to hold that top plate in place within the recess of the slab while you preload. This is an obvious advantage where you've got no floor finishes. The acoustic layer, which you often have between the floor finishes and the top of the slab, can be maintained in place. One drawback is the fire protection is not really a standard detail, and it may be necessary to carry out performance-based fire analysis, such as CFD, like heat transfer analysis, to show that the fire protection can work. Sometimes it's fire protected with fire mortar also recessed within the thickness of the slab. Sometimes it's not possible to access one side of the slab at all, or it's just not viable. For example, if you're strengthening a slab at the top of a tall building, or if there's lots of floor finishes, it's just not practical to install the bolt all the way through. There are some products that can be installed from one side. An example is Worth Relast screw anchors. They're made by a Swiss company called Worth. The anchorage at the top of the bolt, rather than a bearing washer plate, is a screw anchor. The design of these is all based on test data, which has shown up to 40% additional capacity can be achieved. But it's reliant on this test data, and it obviously doesn't have as good performance as if you can go all the way up through the slab. However, if you only need a nominal amount of additional capacity, up to 40%, this can be a good option. Some general considerations regarding installation. A key challenge is avoiding the reinforcement. I recommend scanning the reinforcement with two methods, both using ferrous scanning and ground penetration radar together. This allows both methods of scanning to be cross-checked against each other to get a better estimate about where the reinforcement is located. You need to consider the accuracy of the scans and the reinforcement congestion and the spacing of the bolts to inform how much tolerance you need. It's recommended to allow for additional bolts in case you need to shift stuff on site. And I discussed it before, but you may need propping, or you may need to consider a safe way of installing the bolts if you don't prop it. For example, you could limit the amount of holes you drill at any one time and keep the holes far apart from each other at any one time, and possibly work from further away from the support first, install those bolts first, and then move inward towards the support. Through bolts are a good option as they don't affect the space very much, but sometimes they can be very noisy and disruptive to install, and sometimes they're just not viable. An alternative is providing additional support to the structure. For example, using steelwork. Steelwork can accommodate a variety of geometries to weave in and sort of fit within the limited space inside an existing building. But it's obviously a lot more intrusive than through bolts. Because punch and shear is a brittle failure and the slabs do not deform very much before they fail, it is recommended that the steelwork is stiff enough to actively be engaged to prevent the slab from failing before the steelwork provides support. So either you should make the steelwork very stiff, or you should combine it with jacking, or do a combination of both of those. It is common to use flat jacks, such as the one shown in the picture by hydrocapsule. These are like capsules permanently injected, and they're left there as a permanent part of the structure with the load permanently jacked into them. They're quite slim, up to about 50 millimeters, so they can be accommodated in quite a limited structural depth. Externally bonded reinforcement methods can include carbon fiber, near surface mounted bars, carbon fiber plates, carbon fiber wraps, steel plates. The examples on the left are plates increasing the bending capacity of slabs. The one with the bolts was where the drilling couldn't be guaranteed to not miss the reinforcement, so the carbon fiber is basically substituting reinforcement that might be damaged during drilling to install through bolts. The indicative example on the right is a U-wrapping of a steel plate to increase the shear capacity of the beam. For both steel plates and CFRP, they are bonded with resin adhesive, which has a low limiting temperature, and this needs to be considered quite carefully. If you need the externally bonded reinforcement plates to work in the fire, you need quite a lot of fire protection, probably about 100 millimeters of fireboard, and normally that requires a secondary structure to support it, and it's quite difficult to implement. Another approach, if you do not need the externally bonded reinforcement to work in the fire, you can focus your fire protection on protecting the existing slab so that the slab works independently of the reinforcement plates in the fire case, considering reduced factors of safety in the fire limit state. All of those examples of strengthening I just discussed are very expensive and disruptive in existing buildings. And in some cases, conventional methods could be very conservative and could avoid some of that strengthening or could optimize it. Over the last few decades, computer power has approximately doubled every year, according to Moore's law, and this has opened up a significant opportunity to analyze structures in much more detail and with much more accuracy. At Bureau Happold, we employ a specialist sub-consultant called Astia. They are experts in nonlinear finite element analysis. They use a software called Scientific Toolkit for OpenSeas, which produces a graphical user interface for the OpenSeas software framework developed at the University of Berkeley, California. And basically what this does is it takes this OpenSeas software framework and allows you to visualize all the inputs and outputs and set them out more clearly in order to harness the full potential of the OpenSeas software. I don't know if anyone in the room is familiar with OpenSeas or STKO. We can discuss that at the end, but it's very powerful. So this powerful software can model very complicated nonlinear effects, nonlinear constitutive material properties, complicated stress strain curves, cyclic effects. I'm not an expert on this and I won't go into detail, but it is very state of the art. It uses what's called an implicit explicit solver, where at the structural macro level, it uses an implicit solver, and at the micro material level, it uses an explicit solver and combines the two to create a more efficient and stable solver. Inaccuracies at the material level are corrected during the macro level calculations. And these inaccuracies can be limited by using a sufficiently small time step. If you need more information on this, you can ask Astia, but it's very much more efficient than traditional solvers. The shorthand for this implicit explicit algorithm solver is IMPEX. The nonlinear analysis is not confined to the limitations of conventional analysis. For example, it can much more accurately model compressive membrane action and account for this benefit on the punching, shear, and bending capacities of RC slabs. It can also correctly model triaxial confinement in compression struts. This is very useful, for example, where assessing a transfer slab with closely spaced misaligned columns, which have an inclined compression strut between them. Using simplified strut and tie methods in normal codes of practice, often you have to make conservative assumptions with regard to transverse tensile stresses and the isostatic behavior of the strut, whereas these conservative assumptions are removed by actually modeling the correct triaxial stress state of the strut with the nonlinear analysis. Compressive membrane action and its benefits on bending and shear capacity are well known for several decades. An example of a physical test carried out by Vecchio and Tang in 1989 showed 30 to 40% additional bending capacity in the particular slab that they tested. I noticed in the second generation of Eurocode, there's a provision for accounting for the effects of membrane action on the punching shear resistance. However, it's still very simplified and conservative compared to directly modeling these effects with nonlinear analysis. Relying on this complicated analysis, it is necessary to verify that it gives an accurate result and that it is aligned with physical test data. So Astia have taken some open source test data as well as laboratory tests they've been involved with themselves and managed to replicate these tests. Provided that the material properties, boundary conditions, and loads are all known, the nonlinear analysis can predict the progression of damaged and the ultimate failure in punching shear with reasonable accuracy. There's some animations here. These are animations of the replicated physical tests which were numerically modeled with the nonlinear analysis. The left example is a slab without shear links, and the example on the right has shear links. You can see the distinct difference in ductility between the two slab specimens. On the right-hand side, the shear cracks are much more distributed across the slab before the ultimate failure, whereas without the links, these are much more concentrated and the failure more brittle. The nonlinear analysis allows you to visualize these effects and get a better understanding of the structural behavior. The graphical user interface is also good for visualizing the strains, crack widths, and damage in the various materials within the structure. For example, you can see which longitudinal rebars are engaged and what level of strain they're experiencing. You can also see which links are most effective at resisting the shear and which links are less effective, and it can give you a better understanding about the behavior. Punch and shear capacity is governed by something known as shear crack localization, which in simple terms is the stability of shear cracks which precede the failure. The nonlinear analysis is able to model the progression of these shear cracks before they become unstable, and these are monitored as part of the analysis to estimate the shear capacity. Throughout the analysis, throughout each time step, the dominant shear crack will be monitored, and any abrupt increase in its opening will be identified as a potential instability of the shear crack. Also, the shear cracks are limited by values based on test data. For a slab without links, this is normally about between 0.3 and 0.4 millimeters, and for a slab with links, it's between about 0.6 to 0.8 millimeters or something like that. This is all based on physical test data that's formed the basis of critical shear crack theory, but the nonlinear analysis can model these cracks and how much they're opening up to make a judgment, normally done conservatively, about what the ultimate shear capacity is, and identify the point that precedes the punch and shear failure. This is further examples, also comparing numerical analysis with physical tests, this time for a deep beam. Again, if the material properties, boundary conditions, or loads are known, it can accurately predict the behavior and the capacity. And this is just a further example. The nonlinear analysis can be used to model transfer slabs and better understand their behavior and capacity. Normally, nonlinear analysis shows additional capacity compared to simplified conventional methods. However, this example shows that between the misaligned columns at the edge of the slab, most of the stress is very, very concentrated in a really narrow band of slab. On the left-hand side, you can see that two shear links are engaged. This modeled slab actually has lots of shear links, which are designed in a conventional array, not really appropriate for transfer slabs. If there is a question about the behavior, the nonlinear analysis can more definitively describe the actual behavior and demonstrate whether there is a real issue or not, and whether strengthening is actually necessary and really required or not. If it's required, we have the evidence that it's required, and if it's not required, by doing more detailed analysis, you can save quite a lot of money in disruption. These are just further animations of modeling transfer slabs. You can see the progression of damage, and you can also see how the links are engaged to prevent the propagation of shear cracking. So visually, it's quite powerful. This is not something I've been directly involved with, but I thought it'd be worth including. The nonlinear analysis can be extended further by combining it with monitoring of a real life structure. This is called digital twinning. So a physical structure is modeled numerically, and then this is monitored, for example, with crack monitors, and that monitoring information is fed directly into the analysis model, which effectively creates a twin model of it. It's like having a brain that can sense what the structure is doing in terms of movements, cracking, temperature, etc. This can be used in research, for example, modeling of a half joint. It can be used to create a numerical model that's able to predict the failure and align this with the laboratory data and the monitored cracks. So this is the same half joint, and you can see the cracks that were measured in the laboratory tests, and you can see that the nonlinear analysis is able to replicate these. So in this case, crack monitoring was used on the live specimen, and that was fed in to help predict the formation of cracking. And then that was used to predict the failure of the half joint. And this is another example of a half joint, but this time in a live bridge. The monitors here included accelerometers, inclinometers, gyroscopes, and a thermometer. And the movements of the cracks were monitored in real time, and the trends of the crack opening and closing were reviewed in conjunction with some numerical modeling of the half joint. And this together was used to demonstrate that the crack width limits were met and the observed cracks were within compliance. I believe this kind of method is becoming more common in bridges. It's not really used in buildings. However, there is an opportunity in a building, for example, where a remedial is required and you're not able to go and install that remedial immediately due to licensing issues or other legal issues. This kind of monitoring could be useful to monitor that live structure and ensure that it's behaving in the expected manner and not approaching something that indicates potential failure. That's a way of potentially mitigating the risk in the interim period before the final strengthening can be employed. Computational power is very much still the bottleneck for nonlinear analysis. I already discussed how the solvers can be optimized to make it more efficient with the implicit-explicit integration scheme used by STKO software. This is still very highly computationally demanding, but you can still model punch and shear in a local area of slab. For example, in the screen, this is a submodel of a slab, and in the middle, you have a volumetric model where we are reviewing the punch and shear in more detail. This is a detailed model with full nonlinear constitutive material properties. And then the surrounding structure is simulated with linear properties to create an approximation of the boundary conditions. Employing suitable submodeling techniques, the implicit-explicit algorithm, and a good computer, you can limit the running time to for the examples I showed you to about 8 hours per item. So this unlocks quite a lot of potential to use this technology on real projects and not only for research. In terms of unlocking the potential of this as an industry, I can see this becoming more common as the benefits of it are realized. It is a very niche area and requires someone with very highly academic expertise and a lot of experience. But the number of specialist consultants able to provide this is likely to grow. The fib is uniquely placed to make this successful and make sure that this is used in the correct way. The Fib Model Code 2020 committee, which I understand ASTI are a part of, are developing more standardized methods, including some potentially more simplified methods that could be employed more widely. They are also looking at producing clearer and more detailed guidance on how to use nonlinear analysis and looking to standardize the methods and workflows a bit more across the industry. And I think this is something the institutions will play a key role in. Okay, now the recording's continued. I'll make an important point about nonlinear analysis. It is highly complicated and it should not be relied on blindly. So if we are using this to verify the strength of real existing buildings that people are living in, we need to have a very strong verification and validation culture. So that would include things like benchmarking the results, verifying the results against real experimental data, aligning the results against published research data, making sure that the people carrying out this analysis are suitably experienced and qualified, having a very rigorous QA and checking procedure, encouraging sensitivity studies, for example, where parameters are unknown, or where the result could be very sensitive to specific parameters such as the membrane stiffness or the fracture energy of the materials, it is always recommended to understand these sensitivities. And normally the nonlinear analysis is to confirm an expected and compelling hypothesis. You have a theory about how you think the structure behaves and why it has additional capacity compared to conservative, conventional, limited methods. And the nonlinear analysis is really just to give you more comfort in what you think is already the expected behavior. And often it can also be aligned with parallel cross-checks and simple manual calculations of the capacity to provide further understanding and verification of the results. I'm not sure how much time I have left, but we're nearing the end of the presentation. I think just one more point to make is it's important that engineers have an education of this and its capabilities and its limitations, but also the client should be aware of the capabilities of this. So that would include whether it could help them avoid remedial strengthening works, its limitations, and importantly, it should not be treated as a sort of panacea that will solve all the problems and make them go away. The results don't always give the client the result they want, they just confirm it fails. But much of the time, it could give more capacity, it could save very destructive remedial works in people's homes. And if it's used correctly, it could be very beneficial going forward. That's pretty much the end of my presentation. Thanks for listening. Do you have any questions?